Welcome back to the course of chemical crystallography. In the previous lecture, we just ended with the description of 32 crystallographic point groups, where we talked about the symmetry elements and their orientations, and we have identified some of them with yellow lines, with yellow highlights, and termed them as Lave groups. So now we would like to discuss the stereographic projection of these 32 point groups. What we want to do is we want to represent these 32 point groups in a two-dimensional manner. So for that we will follow the same type of procedure which we discussed in the previous lecture while drawing the projection for the roto-inversion and roto-reflection axis. First, we would like to draw the point group 1. What is 1? We do not have any symmetry in 1, which means we should only draw a circle. Since we will be needing this circle a few times now, I am just making those circles available for us to draw these projections one after another. So the first thing that we would like to draw is the point group 1. Space group 1 does not have any symmetry in it, so only a 360-degree rotation can bring the same molecule or same object back to its original position. So we just draw it as a closed circle and it is point group 1. When we say 1 bar, it means it is a 360-degree rotation followed by inversion, which actually means just inversion. So when we have one object which is a closed circle at the upper hemisphere, we are trying to take its inverse and it comes to the lower hemisphere, and the way the projection is understood as if you have a light at the top, you have the object here, and the two positions, one is up above the equator and the other one is below the equator of this imaginary sphere, are represented in two dimension. So when we have an inversion center at the center, the inversion related object comes in the lower part of the sphere as open circle. The next one that we would like to see is 2. There are two different ways one can draw a twofold. If the twofold is in the plane of equator or in the equatorial plane, then what happens is, if this is a sphere, if a twofold is there from front to back, the object which is here gets rotated by this twofold and comes to the lower hemisphere on the other side. So the the closed circle on the right becomes open circle on the left. By this twofold axis. One can consider the twofold to be along Z, which means we may have the twofold in the middle of the plane of projection. So in that case, we start from here. So this is a twofold. My object is here, when it rotates, it still stays in the upper hemisphere but comes to the other side of the upper circle. So, the object which is here on doing a twofold rotation comes there and still remains a closed circle. So, this is another representation of 2. They are one and the same. What is 2 bar? A 2 bar operation means you have a twofold axis and inversion center. So, you start from one point here, do a twofold rotation, followed by inversion takes it exactly below the original point. So, anything coming exactly below is equivalent to a mirror operation. So, 2 bar should look like this. The closed circle and open circle are at same place because you have this twofold axis, you are rotating the point by 180 degree and taking the inversion, it goes there. So, this inverted point comes at the same place of the original point, and that is why this 2 bar is equivalent to a mirror. Now, let us see the point groups 4 and 4 bar one after another. When we say a point group 4, it indicates that it has a 4-fold axis of symmetry, at the middle, as a result, the object is, this is the 4-fold axis, the object is here, it rotates by 90 degree, 90 degree, 90 degree and goes back to the original position by 90 degree rotation, and it always stays in the upper hemisphere. So, therefore, all the 4 positions are field circles. But in case of 4 bar, the situation is slightly different. When you have this open closed circle, what you do is rotate by 90 degree and simultaneously invert. So, it comes to the lower hemisphere. So, the closed circle after one round of 4 bar becomes open circle in the opposite side. So, from here the point should have come here as of a closed circle, but then since this is a 4 bar which is a simultaneous operation, so we do a 4-fold rotation followed by inversion, it makes it as open circle. Similarly, you rotate it by 90 degree and invert it. We started with open circle, this must be a closed circle. Now we start with this closed circle, rotate it about 90 degree and then invert it. We started with closed circle, so this should become open circle. So now you see 4 and 4 bar are different in their representation. What happens to 4 by m? The point to be noted here is when we say 4 bar, it is roto-inversion axis. So, rotation and inversion takes place simultaneously and then we identify the point. But when we write 4 by m, it means we have a 4-fold axis and a mirror separately. So, we should have points corresponding to 4-fold and then apply the mirror to all those those points generated by the said fourfold. So to do that, we divide this circle in 4 parts, draw the fourfold in the middle, and then start with the closed circle. We do a fourfold as we have done before on the left hand side, and it generates those 4 points because of fourfold. And now when I am saying that 4 by m, in the previous lecture I have talked about this 4 by m means a fourfold is along C and mirror is perpendicular to that fourfold. So the mirror plane is the plane of this particular circle. So when you have mirror plane in the plane of the circle, then all these 4 points which are closed circles will be reflected in the lower hemisphere. So one open circle has to be drawn at the same place. So this then represents 4 by m. What will be 4 by m, m, m? In the textbook, you will see that it is written as 4 by m, m, m. It actually means it is a 4 by m operation, and then there are 2 more mirrors perpendicular to that first mirror which contain the fourfold axis. So now to identify that, we first draw what we have seen in case of 4 by m. What we have seen in 4 by m is this, which is there on your left. Now when we are saying that there are 2 more mirrors containing the fourfold axis perpendicular to the previous mirror, then the 2 mirror planes should be this one and that one. So now if we try to operate these mirrors on the points that have been generated, we should simply get one more set of closed and open circle because of that mirror, and because of this horizontal mirror we get one point here and we get the corresponding point there. So this represents 4 by m, m, m. The next one in 4 we would like to discuss is 4 bar 2 m. So now it is a combination of 3 symmetry elements. One is 4 bar, which is along the C axis, Z axis, a twofold which is along A or B, and a mirror which we will see gets generated between the A and B like a diagonal plane, that is sigma d. So to start with, what we should generate is the 4 bar. As we have seen in 4 bar here on the left, we should first generate the corresponding 4 bar. Now I have a 2, which means this 2 is either along x or y. So if I assume that 2 is along this direction, which is here, what I end up getting is this twofold which we are thinking is along the equatorial plane, and the point above the plane on application of this twofold goes below the plane. So as a result, which is open circle here, closed circle here becomes open circle. This open circle goes to the other side and becomes closed circle. This open circle comes to the other side and becomes closed circle, and this closed circle coming on the other side becomes open circle. See what has happened. By default, by applying one twofold in one direction, it has generated another twofold in a perpendicular direction. What else has happened? It has generated a mirror plane bisecting these two twofold axes. Two such mirror planes have already been generated. So we have two twofolds, one along x, another along y, and then we have two mirrors bisecting the x and y direction as this and that. So this particular diagram indicates the point group 4 bar to M. Now we will try to see some of the point groups which involve 3 and 6. So now let us start with simple 3. What is a threefold axis? It gives you a 120-degree rotation. So whenever we try to draw 3 or 6, we should divide the circle in 6 parts. That means we draw 3 lines like this. We have the threefold axis in the middle. We start with one object here, and the threefold axis suppose is along z, then the point rotates like this by 120 degree and comes here, by another 120 it comes here, another 120 it goes there. So by doing such operation, it goes at those 3 places and it is just 3. The next one that we would like to draw is 3 bar. What is the difference here? It is 3 and inversion simultaneously. So once again we should carefully divide the circle into 6 parts, and we should start with the closed circle. So now when we are doing it 3 bar, it should be a rotation followed by inversion and becoming an open circle. This is my 3 bar axis. So now again we rotate from this point, 120 degree rotation brings it at this point, and then if we do an inversion, we started with open circle, we should end up getting a closed circle. Then we continue this operation, 120 degree rotation followed by inversion becomes open circle. Start with open circle, 120 degree rotation followed by inversion becomes closed circle. once again 120-degree rotation followed by inversion becomes an open circle. So this is the representation of 3 bar. What happens when we draw 3 bar M? We can straight away draw the 3 bar first. And when we are saying this as M, this M is not perpendicular to 3 bar, it is along the 3 bar. So we can consider this M as one of these lines. When it is 3 by M, then it is perpendicular to 3-fold, but when it is 3M or 3 bar M, that mirror contains the 3-fold axis or 3 bar axis. So by doing this mirror operation, what we get are just the mirror images of those points. See what we have obtained. By considering one mirror along one of those straight lines containing the 3-fold and then applying the corresponding mirror, we have generated a mirror here and we have generated another mirror there. So this particular diagram represents 3 bar M. What will happen if we want to draw 3M? Once again we divide it into 6 parts. The 3-fold axis is in the center and then we'd like to draw the points. So first we draw 3 because these two are not simultaneous operations. So we have just drawn 3, and when we write M, it is the mirror containing the 3-fold axis. So this could be a mirror like that. So this mirror reflects this point to the other side, this point on left hand side, this point on left hand side here. So what is the result? As a result, we see that it has given rise to these lines which we initially had drawn to make it 6 parts are also the corresponding mirror planes. Now let us try to draw 2 point groups, 6 bar and 6 by M, M, M. Sorry. We should draw 6 by M and 6 by M, M, M. So when we again say it is 6 by M, it means we have a 6-fold axis along Z. So we again divide this into 6 parts. The 6-fold axis that we are talking about is here. So my object which is sitting at this point, I am rotating it by 60 degree, it goes at all the places at rotation after rotation of 60°, and it does not change its nature because it remains always in the upper hemisphere. And then when we say by M, this 6-fold is here and the by M mirror is perpendicular to it. So the mirror plane which we have here is the equatorial plane, which is the boundary line of this circle. As a result, these points will go below the equatorial plane after the mirror operation. So the open circle and closed circle both will come at same place. So now you can easily understand that what will happen if we do 6 by mm. So we again divide it into 6 parts. The 6-fold axis is at the center, and then I will first draw 6 by M as it is drawn on the left hand side, and then the two mirrors that we are talking about are these two mirrors. Maybe even if we just draw one, it will generate the other mirrors. So this one generates the object there, this mirror reflects it here, the mirror reflection of this comes to the other side, the mirror reflection from this point goes to the other end, the mirror from here comes at this point, this mirror comes on this line. So as a result, what has happened is it has generated the other mirrors as well, and you can see there is a mirror in between. So this is the representation of 6 by mm, which in textbook you will see is written as 6 by mm. Now we will do two space groups which are very similar, but they belong to two different crystal systems. As you know, 3,2 belongs to trigonal system, while 2,3 belongs to a cubic system. When we say 3,2, we first should draw a threefold. What is a threefold? We have already drawn it on the first left hand top corner. So the threefold can be drawn very easily. And the twofold axis that we are talking about is perpendicular to this threefold, which is here. And there are three such twofolds which are like that. So now by doing this twofold operation, the closed circle becomes open circle, this closed circle on this side becomes open circle, this closed circle becomes open circle on that side. So this diagram represents a simple 3,2 point group. But 2,3 is different. 2,3 is a cubic point group, and in a cube what you have are 4 threefold axes. If you draw a cube and then from every corner to the other other corner along the body diagonal is your threefold, and there are 4 such threefolds, and the two folds that you have are along the faces. The center of the faces, you have these two folds along the center of faces. So drawing this 2,3 is slightly difficult, so I am drawing it slowly for your easy understanding. First, I am dividing it into 4 parts. Then I am joining from top to bottom with a curved line. I am joining again left to right with a curved line, and then joining these points across. So now, since we have 4 threefold axes along the body diagonals, we write those threefold axes at those 4 points of intersections of 4 lines. So now if we start putting our points, the objects, suppose we have one object here, we do a threefold rotation, the object comes here. We drew another threefold rotation, the object comes there, about that 3. Now, every one of those lines which we have drawn, these lines correspond to a twofold axis. So now what has happened is, the closed circle on the right on 180 degree rotation becomes open circle on the left. So this twofold, this closed circle on the right comes here and becomes open circle, and this comes here as open circle. So the top portion is done. Now once again, this particular line which we have drawn also represents a twofold. So when we do this twofold on all the 6 points that we have on the upper portion, the closed circles will become open circle and the open circles will become closed circles. So then this particular diagram which we have now generated at the end is the stereographic projection of point group 2, 3. I understand this is difficult and one can only draw it when you have done this many times. You should try to practice these 2, 3, 3 to 6 by mm and all these point group drawings yourself to be able to draw it easily. So in the next class we will continue with the crystallographic planes, directions, Miller indices, etc.